back. So today we're going to be talking about triple integrals in cylindrical and spherical coordinates. So like we had with double integrals, sometimes certain integrals are easier to calculate when we go to another coordinate system. Now in R2, so the xy plane, we had two coordinate systems. We have that Cartesian, or what your book calls rectangular, and we have the polar coordinate system. Now in R3, okay, three-dimensional space, we have two other types of coordinate systems other than our standard Cartesian coordinates, and that's cylindrical and spherical. So that's what we're going to be talking about today. This video might be a little bit longer, but we're spending our whole week on these two coordinate systems, so it should even out. All right, so let's go ahead and get started. So cylindrical coordinate system, kind of like what it says in the name, it is related to cylinders, and I'll show you how. So first, let's go ahead and talk about really quick. I didn't know I could do that. So let's say we have R3 here and we have a point X, Y, Z. So again, remember, what does this point mean? This means that, let me go ahead and write all this stuff down. Okay, so this point here represents, all right, we go X units down the X-axis, then we go Y units down the Y-axis, and then we go up Z units, and actually I'm going to move that point right here. Okay. So that's what these coordinates represent, X, Y, Z. And in this case, you can sort of think about X, Y, Z as sort of living on this cube here. Hopefully you guys can see that okay. Which I didn't really bring up with polar coordinates in that you can sort of envision your point X, Y living on a rectangle, but this is kind of what we have in Cartesian coordinates, though. You're sort of living on a box, okay? Now, cylindrical coordinates changes that a little bit, and it says, well, instead of envisioning your point living on a box, let's envision it living on a cylinder. Okay, so let me get rid of the box here. Okay, so imagine it's living on a cylinder instead. Okay, so like we have in our picture here on the right from your book, again, imagine that there's a cylinder here. And these coordinates are telling you where on the cylinder your point is. Okay, so that's the visual representation of the cylindrical coordinate system. So cylindrical coordinates are given by R, theta, and Z. So what's super nice about this coordinate system, nothing really happens to Z. Z is just Z. The only thing that really changes your X and Y, and notice R and theta, we're using R and theta because these are the same R and theta that you would have in polar coordinates. They mean the same thing. Okay, so if you were to project this point down into the XY plane, R and theta are the same thing they would mean back in polar coordinate land. Okay, so that's our coordinates. In class, we're going to develop the relationships or the conversions. So I don't want to spoil that here in the video. But what's nice about the cylindrical coordinate system is all the relationships you already know from polar coordinates. Okay, so to convert from Cartesian to cylindrical. Oh, notice your book is using Cartesian. They're back on board. In any case, I think that's because rectangular coordinates only works for R2. But in any case, if you're converting from Cartesian to cylindrical coordinates, okay, X is equal to R cosine of theta, Y is equal to R sine of theta, and Z is equal to Z. So again, that's one of the nice things about that third coordinate. It stays the same. But again, notice that we have the same relations that we did in polar coordinates. So really, cylindrical coordinates are the polar coordinates in R3. Okay. If we're converting from cylindrical to Cartesian coordinates, then we use the equations R squared is equal to X squared plus Y squared. Tangent of theta is equal to Y over X, and again, Z is equal to Z. So not too bad. Okay, so if we're integrating in a triple integral in cylindrical coordinates, okay, so again, we have to sort of be careful. If you remember back in double integral land and integrating in polar coordinates, remember that when you did your conversion of your function, okay, into this, you also had to multiply by R. It's the same thing with cylindrical coordinates. And again, it's because we're changing our rectangular boxes. Okay, not the worst box I've drawn. Whoops, let's not forget that. So we're changing our rectangular boxes to these, I don't want to call them cylindrical boxes, but for lack of a better word, that's what I'm going to say, cylindrical boxes here. And so our volume formula is changing, and so that's why we're picking up this R. But in any case, to convert from Cartesian coordinates to cylindrical, you use your conversion formulas. X is equal to R cosine of theta, Y is equal to R sine of theta, and Z is equal to Z. And then make sure you multiply by that extra factor of R, because again, when we change this coordinate system, we're changing how we're breaking up our solid. And the volume formula is a little bit more complicated. So in any case, I'm going to erase this. So again, essentially, pretty similar to polar coordinates, right? Except we're in a higher dimension here. Okay, so let's integrate this function at 8 plus x plus y on the solid bounded above by the paraboloid 16 minus x squared minus y squared and bounded below by the xy plane. Now, like we had with double integrals, if we want to integrate over this region, what we have to do is we have to parameterize this region. Okay, so we're first going to do that, and then we're going to convert to cylindrical coordinates in this case. So let's go ahead and draw the region. Okay, so here's our xy plane, and here's z. Okay, and now let's see, we're bounded below by the xy plane, so that's this plane right here. Okay, so I'm going to erase that. Good, so one part is done, and now we are bounded above by the paraboloid 16 minus x squared minus y squared. So that kind of looks like a bowl that we flipped over. Okay, kind of like that. Okay, so let's go ahead and parameterize this. So notice that if I take, and by the way, it's the whole solid here. So imagine a filled-in bowl, not just a regular like cereal bowl or something. Okay, so let's parameterize this. So notice that any point in here, well, if I take a slice, I should say, okay, notice that z is going from the top of the bowl to the bottom. The top of the bowl here is represented by 16 minus x squared minus y squared. And the bottom, since it's just the xy plane, that z is equal to 0. Okay. All right. Now let's go ahead and project into, so imagine we take our bowl and we smash it into the xy plane. So let me erase this. So guys, imagine, I want you to take your thinking caps and keep in mind here, we have that 16 there. Okay, that is going to come into play. But again, imagine taking this bowl and smashing it. What do we get? Okay, so in the xy plane, we get a circle of radius 4. Okay. All right. And we get the whole circle of radius 4. Okay. So what is, and we'll go ahead and slice it like this. Okay, so then y would be going from square root of 16 minus x squared, so that's the top part of the dome, minus 16 minus x squared. Okay, so that takes care of y here. It's going from this point to this point. And then as y is going from that, what's x going from? X is going from here to here. And remember, this is a circle of radius 4, right? So x is going from 4, or negative 4, to 4. Okay, so there's our parameterization for this paraboloid that's been cut surface. All right, or solid, I should say. Okay, so now let's go ahead and convert to cylindrical coordinates. So remember our conversions. We have, here, let me actually go back. Okay, and let me erase this for us. All right, so we have x is equal to r cosine of theta, y is equal to r sine theta, and because we're going to need this, notice that r squared